My name is Festus Hategekimana. I do security architecture development work at Solidigm. Fred Knight and myself have been helping with Keyprio specification development across both NVMe and TCG for the past few years. And now that both organizations are releasing the final version of specification, we figured we'll use this time slot to give some recommendation to development teams that are looking to start deploying the technology. Fred, as you can see, he can make it today, but we work together on slides, should be able to cover his portion. The agenda of the talk today, we're going to start with a quick introduction of what Keyprio is and what benefits it provides, and then we'll dive into actually how to use it. We're going to spend some time on the one-time setup that the host has to do, and then spend the majority of the time on the host management of the source device key cache. And part of that, we'll look at how the host sets up the keys into the device, how it selects the key to use to associate with different IOs, and how to replenish, reclaim some of the key slots, and then we conclude with how to change the life cycle of Keyprio in a storage device. All right, for a quick introduction, Keyprio, for folks who are not familiar, basically what Keyprio does is fundamentally brings hardware acceleration, storage device encryption hardware acceleration to host managed encryption service. All right, for folks who are not familiar with what host managed data encryption service is, it's basically when the hosts control the entire life cycle of the data encryption keys that are used to encrypt the host data. Quick example, in that example, basically the host will have its own keys that it associates with different storage objects. And the startup time, the host will provision the keys into the storage device. And then in runtime, the host will associate keys with different storage objects. So each key can be uniquely associated with a storage object. And then during the read and write commands, the host basically sends the data and point a reference to the key that the storage device needs to associate with the storage object. So when you have your data stored on the NVM, you could basically have dynamically sized object, each individually encrypted with a key that is only known by the host. This provides a great improvement, obviously, in terms of throughput on the host side, since the host doesn't have to do it like they do today with encrypting on the compute side. You basically parallelize your encryption on each SSD entire your fleet, and obviously you have increased data protection since the security, the encryption keys themselves are not stored on the storage device, always reside on the host side in some specialized hardware secure modules. Right? I think we're going to stop here with a quick introduction, but for folks who are interested in pursuing further exactly the architecture and various architecture elements of Keyprio, Fred and I have done quite a bit of talks on this. You can find a few of them on FMS or CNES DC websites. I want to jump quickly into actually how to use it. So the first thing, if you do development, you probably want to figure out if you're system person, sampling vendors, you want to figure out what type of Keyprio flavor does the device support. So from NVMe side, you have discovery capabilities in terms of finding out which whether Keyprio applies on entire subsystem or if it can be turned on per namespace. This is very useful, right? And we'll see later the reason why you want to be able to figure out whether the capability applies across the entire NVM subsystem or per namespace. The other capabilities you can find out are whether the amount of key tags that you can think of as the number of the keys, encryption keys you can have active at the same time per namespace and per the entire, obviously, controller. And you can find out the level of data access you can do with the encryption. On the TCG side, we figure we'll do discovery on both sides to kind of bring some flexibility on the host storage software development side. On TCG side, you can also find out some of the same things in terms of the number of keys that the device key cache support, but also the number of active keys that you can have active at the same time. And obviously the security properties for how you want your keys protected across the interface, whether, how you want them encrypted, the length of encryption keys, so all that good stuff. Obviously you can do namespace level discovery, but you can do also the NVM subsystem level discovery. Part of setting up, so once you figure out what flavor of Keyprio you want, the next thing is then to turn it on, right? So today, the presentation uses real APIs that, are available in standards that are published today. The basic idea is for folks who have interacted in any of the self-encrypting drive protocol, the basic idea, you basically use your SAM activation command, right? But depending on the flavor of Keyprio the device support, the way you can think about this is you're transitioning the management of encryption keys from the device to the host, right? So if Keyprio covers the entire drive, aka if the host, the keys that are needed to perform encryption and decryption come from the host, if you turn on Keyprio on a device that where Keyprio covers the entire devices, then that device key cache, effectively what that means is you don't, when you turn it on, there's no host keys available, right, in the device key cache. So that's important to know, because if you think about folks who interact with things like OPPO, you can generally turn on OPPO when you have your operating system going and applications going. With Keyprio, you got to choose, whether you want to turn it on per namespace or per the entire NVM subsystem. Per namespace allows you to have bootstrapping namespace, so you can still access the data on that bootstrapping namespace while you turn on Keyprio and the rest of other namespaces. So once you've turned it on, the next is just configuring it, and what that entails is basically setting up the number of keys. Obviously, the device manufacturer has the upper limit on how big the key cache is, but the to dynamically allocate keys per namespace, this is in host hands. So part of the configuration is allocating how many keys that you need for a particular namespace. And whether you need, certain type of security protection of the keys when they're being sent across the namespace. I think some of the application note document have been published by, TCG. They have some command tokenization detail exactly to show you how all this is done, and I believe some of those documents are in public review today, so very accessible to anyone. But once you've done your one-time setup, then you're done. The rest is just the host managing the key cache. At startup time, the host provision the keys into the device. It's a simple command, simple inject command. And the way we've choose to format the keys, we use KMIP, since a lot of the host managed encryption service today use KMIP as the key formatting infrastructure. So we allow the host to create basically a KMIP payload that has the actual key data, the key material, cryptographic attributes of the key, of course, the length, and plus the namespace that the key is intended for. Additionally, we need to provide a way to define, to say, for this particular key, and put in a key slot, or key index A or B, so that's called a key tag. So those attributes alongside the key material, they're both sent across the interface. We allow batch items. So what that means is you could basically populate the keys for entire NVM subsystem in a single command. It's a stateless command, so there's no sessions. Folks familiar with TCG session, I think probably going to enjoy this. There's no session. It's a simple send command, and you get your response, right? So at that point, the device key cache, if you see on the right, the device key cache will be populated by the keys that you sent in, and then it's time to use them. TP4055 is now ratified by NVMe. It extended NVMe write commands, provided basically a field to specify that you're using Keyprio, using a key tag, and this is the particular key tag you want to associate with the data type that are inside the write command, right? So it's the slide have the actual details, but the TP 4055, I'll refer you to that, has the exact detail per write command. So once you specify that you have the key tag, so all the device has to do then when the host issue a write command or read command is to use that key tag and namespace ID to do the key lookup in its key cache. So once it finds the key associated with the data in a write command, and then it use that key to encrypt and store the data to the NVM. I have as you can see on the slides, it's maybe hard to read, but I use the color coding to basically signify different keys. For example, say first command in a queue, you have a write to namespace ID 1. We have a key tag, and we're going to use key tag 1. But as you can see in the namespace ID 1, you already have the same key tag 1 and the key. Say the key ID is 3, so that's what the device will use to encrypt. Similarly, on the second write command, but let's look at the maybe the third write command, color coded in green. So that one host wants to use key tag 2, but when they provision, when the host provision the key, there's no key associated with key tag 2 for that namespace 1, right? So what that means that request is going to fail, and you get specific error that says invalid key tag. So it's pretty much referencing a key, and the device know how to look up using that combination of the namespace and the key tag. The host can update the key tag anytime, the key cache anytime. They can provision new keys into the key cache, and what that does is basically updating the key cache is nothing. It has no effect to the actual data that's been written using the keys that are being replaced out of the key cache. Right. So in this example, for example, the host can just choose to provision a new key in for namespace ID 0 key tag in the first key tag, and that's just gonna update it to say from key ID 0 to key ID 1, and the host can then go ahead use that newly provisioned key to write its data. And what again, updating key cache. This is one of the other points of confusion we get. Updating key cache is basically just a swap of a key, but the data written by the previously injected keys always stay there. So that allows actually, the way you can think about this, the host isn't constrained on the size of the key cache. The size of the key cache just reflect what you can use actively at runtime at the same time. But if you want to swap to new keys, you can always swap in and out keys without no problem. The other question we get around this is your performance concern if you have to swap in and out different keys. The way to think about it is basically, if you have to access data that's protected by a lock, right? You need to provide some kind of authentication to unlock, right? And then to perform the read or write. It's kind of the same thing, right? Ultimately, you need to inject the key to get the data you want. So I think after this, the less is management stuff that the host, if host wants to be able to lock the key cache for a certain amount of time, they can easily do that by issuing a command per namespace or entire NVM subsystem to clear the key cache. You may clear a particular key slot. You also you have the flexibility to clear keys belonging to a particular namespace or keys belonging to entire NVM subsystem, and then reinject, of course, when you want to have access to that data. Disabling Keyprio, it's more similar to basically what you find with self-encrypting drives today. You issue a command. Mostly folks are familiar with revert command. It's basically the same thing. Obviously, here you want to make sure that if you revert it, right, if you were to reinject the same keys, for example, if the key was to leak and you want to reinject the same keys, you don't have access to that. This is very important. Revert needs to ensure that the management of encryption goes back to the storage device. So if you were to reactivate and insert the same key, the data previously written by keys supplied in the previous sessions is not going to be accessible. So anyone who, if were to happen that the keys were to leak from the host side, a revert will ensure that if even those keys were to be reused out of band, there's no access to the data written by those previous keys. To conclude, the specification status, I think NVMe ratified, by the time we submitted the slides for FMS, TCG, they were in public review, but they concluded they're doing the final publication for those two documents. TCG SIS specification already, that's the spec that defines the interaction of NVMe and TCG. That one has already been published since last year. So I think all the documents are available, and there's an application note to kind of show the exact command tokenization from all the way set up to usage and runtime. So folks looking to start deploying the technology, I think they're in a treat for this. I think I'll stop here for questions on both Keyprio and FDP. Thank you.
Good presentations, guys. One FDP question, one Keyprio and IO question. FDP question, do you have some kind of magnitude, you use case guys, for how many open handles you want at one time? How many active handles you want at one time?
Go ahead. Okay, so I guess I got elected for this. So I am advocating for roughly 8 handles will handle a large portion of use cases. As far as magnitude, there are a lot of use cases that need much fewer than that as a rough ballpark.
Okay.
I can add, there was an open source presentation earlier today. It showed how CacheLib is getting updated, and it doesn't require very much. A little bit of separation makes a lot of difference.
Okay, so 8. You're thinking 8.
8 is a rough ballpark. I know some people be higher, some will be lower, but it's a starting point for discussion, if that helps.
Yeah. Chris looks like he wants to say something.
There's a distinction between RUH and reclaim groups, right? So if you're in a mode where you have a reclaim group per die, then that 8 gets multiplied by however many reclaim groups you have, and so you have it's a trade-off, right? Because you don't have super blocks, so you wouldn't have RAID, but you have a lot of ability to you kind of maybe a 100x multiplier on how many handles you can keep.
And the motivation of my question is the underlying housekeeping, right? Yeah, that it gets hairy the more of those you got.
Yeah. I think at an individual die level, you start getting lots of handles open. Now the overhead of just the blocks sitting there waiting, that's a factor too, right? Yeah. So,
and then Keyprio and IO, are there any constraints on granularity of Keyprio and IO? Is it a single logical block at a time is perfectly okay, or is there something where the drive can say, I need you really to do this on a course of granularity in a logical block?
Very good question. I think there is a part of the discovery. There is each device report the minimal granular access you can do, either 4K or 512. But in terms of associating the keys with actual storage object, there is the host controls how big or how small you want it. That's one of the big benefits here compared to existing solution where you have fixed ranges that you have to work with, fixed partitions that you have to work with. With Keyprio, you have the host can dynamically size the objects and associate equation.
Yeah. Okay. Thanks.
Hi. I have a couple of questions on the FDP presentation. And in the FDP, do you see the more use in the high performance, low latency drives or in the higher capacity, low cost drives? That is the first question. And then the second question, if it is on the higher capacity drives, the map table requirement is much less on the ZNS side. So would you prefer a much lower cost, that kind of a drive, or would you still prefer FDP? And then the third question is, because you're representing the Google, Meta, everything, if you are given a ZNS drive, would you ever use it, or would you stick with the FTP?
Maybe you want to start? So on the high performance side, right? I think it's pretty clear, that FTP is kind of, especially with the virtualization capabilities you can get by having multiple namespaces with handles allocated per namespace and configurations like that. There's a pretty compelling case there. Then you were asking a question, I think, in the middle about larger capacity drives, and it is, and kind of versus ZNS and whatnot. I guess I would say that there's some value to fungibility, right, and configure multiple. I think with ZNS, you're sort of locking yourself into something early in life, and so maybe it comes down to flexibility versus if you're really just going to go for the high capacity use case. I think there's also a question about whether we'd ever use DNS or not. I think maybe I'll let Ross handle that one.
Oh, I get the tough question. So, a couple things. I think there are use cases both high capacity and there are use cases for high performance. High capacity, a good example of this is disaggregated storage. You have a storage stack that knows what applications it's talking to and how to group the data. And that, many people have those stacks today. So migrating the FTP is not a very difficult task. So in the high capacity case, it adds value in that area. And so it spreads both spectrums. And one of the key pieces of this is it's backwards compatible. So you use your conventional drives the way you do. And the point you have FTP in a state that you feel you're able to go to production, you can turn it on as opposed to committing, I'm going down a path and hope it works out. Okay. Also, it's a standard device. And the complexity on the device side is very low, all things considered. Meaning the big two changes, I talked about this in a presentation yesterday, two big device changes. So typically devices build their backend with super blocks, meaning it's a bunch of blocks that may have XOR over or something. And the device picks what super block to put the data in. Now the host provides a hint where to place that. That's one change. And the other big change is the device advertises the size of that super block. So the device side, the changes are very limited. Security, read, write, there's an optional pointer, but all these other things, trim, deallocate, they work the same way.
Okay. So you see the use case on both the high performance drives and the high capacity drives for FTP?
Yes.
Okay. And then the third question?
What was it?
Sorry,
because you're proponents of FTP, if you are given a drive with the ZNS, would you ever use it or you will not use it at all?
I think it's a different technology with different needs, and so that's I think about all I'm going to say about ZNS.
So yesterday, Javier Gonzalez from Samsung gave a presentation where he went over ZNS and FTP, and he identified, that there are some use cases for ZNS, and then there are use cases for FTP. ZNS requires sequential writing. And if you have a sequential write, you can do that. But what they're saying in the workload is not everything's sequential, and it's hard, and FTP has a place for that. And so in the ecosystem, we're trying to figure out what meets everybody's needs in the whole world, and there's a balance here. And what we found is, in some cases here, ZNS didn't work out. Yeah. So we needed another way to do it. And so that's where we are today.
Okay. I think maybe to summarize, I think, and I'm not going to try and put any hard numbers on this because it's kind of, but I think ZNS, there's a bigger initial investment. You got to, depending upon your stack, it might not, maybe big. The delta is all dependent on your situation, right? But then, potentially it's absolute then, right? You're pure sequential, and if it forces you to be in this WAF one world. Although you can argue about that because there's you end up doing copies in the host. It's just you're moving the WAF around, right? Whereas FTP it allows incremental investment, and maybe you get a big chunk of the value with very little investment, like 80 or 90% or 100%, depending upon your workload. Again, it's variable in your situation, without having to kind of re-architect or, if you've got a system that's not doing sequential writes, and the workload is such that you get like 95 or 99% of the value with FTP, it's a clear value proposition on that side, right? I don't have to rewrite the world, and I get almost all the benefit, right? If you're in a situation where you're already sequential writes and you've done all this investment, and that incremental, last whatever percentage of WAF is critical, then so that's the extreme case for
I mean, with the bigger capacity, you saw that yesterday 256 terabyte, and then it keeps going up actually, and then the DRAM cost goes up, and then with the map table much less required in the ZNS, there is a huge cost advantage.
Yeah, I guess, okay. I don't know if you want to.
I was going to say the size of the map is unrelated to FTP. Whether you're 512, 4K, 16K, 32K, 64K, I use FTP just works.
Yeah.
And so the size of the map is unrelated from a technology point of view.
Okay, thank you very much.
Thank you. I see we have another question here.
I have one question for the FTP. I'm still a little bit confused regarding the concept of reclaim group. Reclaim unit, understand it's more mapped to like super block or couple of erase blocks. But what is the purpose for the reclaim group?
So a reclaim group is really the primary goal originally in the standard is to capture the two different configurations where you would want, in a super block, a traditional drive, you got a super block. Your reclaim unit will be a multi-plane erase block on each die, right? Aggregated together, subtracted out the space that's required for parity, right? That would be, what you'd expect, or what I'd expect, maybe not. And then in a scenario where you're not doing super blocks, you'd expect to be reclaim groups. The reclaim group count advertised would be the number of dies you have, and a reclaim unit would be a multi-plane erase block on a given die, right? Sure.
Let me add. So every drive has some unit of which it garbage collects. It might be a single die unit. It might be a stripe of dies, but some unit. And a reclaim unit is that unit which a device garbage collects on.
But reclaim group is
and then
is different.
If there's parallelism above that layer, then those are reclaim groups, right? So if my unit of garbage collection is a single block on a single die, and can operate parallel and independently with other dies, right? In that scenario, then each of those other dies is a reclaim group. If I have super blocks but they're small, like they're across 8 dies, right? Now anyways, it'll get complicated, but it's just essentially a kind of a self-similar layer above, right? So the simplest configuration, like Mike was kind of showing, is a single reclaim group from a understanding it standpoint, right? Then all of your reclaim units are all in one big pool, and essentially it's they're in the same coming out of the same pool of backing demand. So
okay, got it. Thanks.
Hi, I'm Chris. I have 2 questions for the FDP and for the presentation, Festus. First question is that what do we need to consider during live migration between FDP to another FDP or FDP to a conventional? Do we have to consider all those hints, or even the geometry of those resource group and resource unit? That's the first question.
So live migration has nothing to do with FDP. FDP is about writing logical blocks to the drive in efforts to align data so no recopying during garbage collection has to happen. Live migration is about taking an initial static view of a namespace and copying it somewhere else, and then tracking the LBAs that are changed by the VM that's still running while you're doing it, and tracking them over there. Those are all read operations from the thing doing FTP. Now, it's really host managed on live migration. And the live migration, if they're moving somewhere else, if that device is doing FTP, then they would do writes on that side to take advantage of it. So they're really independent. They're architected to be independent.
But they do have to be FDP both from the target as well?
Absolutely not.
Oh, okay.
If you want to take advantage of WAF, you can go FTP to FTP. If you want to go from an FTP device to a conventional SSD, you're free to do it.
Okay. Thank you.
So it's on live migration, one guy's doing read, another guy's doing write. The guy who's doing write has to take advantage of any technology we have there on doing the write. So they're totally independent.
Thank you. The
And it's
second
a beautiful thing to be independent.
Another question I have is about for the encryption. Does it require any CPU capability to be used on confidential computing for data in use?
For data in use?
Does it require any capability on the CPU side to be able to utilize those those features that you presented in a use case where we have to do a confidential computing for data in use?
Right. No, Keyprio doesn't. Can you hear me now? Right. So I think the question is, does Keyprio impose any requirements on the host CPU or in confidential VM?
For confidential computing.
Confidential computing.
Mhm.
There's no requirements. Doesn't impose any requirements on the host CPU for confidential computing. The part of the host managing encryption keys, however, since the host has to orchestrate the transport of the keys from wherever they could be stored, from some key management server to the storage device, you could argue that you need to have good runtime security on the host side, right, to make sure that as the keys are being encrypted and sent out across the interface to the drive, that there's no leakage. That's about of a requirement that you could say to impose, but that exists today if you still have to do host managed encryption. So natively, Keyprio doesn't add anything.
Okay, thank you.
So for FTP, when implement the FTP, do you see any challenge or downside on other area? For example, take care of the PLP.
Okay, great. By the way, lots of good questions about FTP today. Hopefully I'm talking better in the mic so people can hear. I see a thumbs up. It must be better. So first question is you ask about challenges with FTP.
No, I mean in other area. For example, PLP, you need more resource.
Okay, so PLP, good question. The more handles you have, the more open blocks you have, and it depends on how you handle power fail with that. There are cases where you may want more PLP. That doesn't mean more than what you're doing today in standard drives. But if you were to add lots and lots of handles, that might encourage you to add more caps. But I don't see a need to add more caps than what is typically done on drives today. But it is different from the point of view that on unsafe power down, you will have more open blocks. You'll have the same amount of data to flush out, but it may be distributed slightly differently. Does that help with your question?
Yeah.
I want to add to that. FTP does account for allowing an FTP configuration to say, hey, host, you required me to buffer more data than I have in my power loss protection. And the FTP configuration will advertise it, and it's to tell the host, if you use this FTP configuration, now you have a volatile write cache, and you need to flush out your data to guarantee your writes. So we built that into architecture. Whether the ecosystem is going to actually employ that, it gives us the option to say, hey, I have this memory on there. Could we experiment and do some stuff? Or maybe we really have a real use case. The way it works is for backwards compatibility, if any FTP configuration does support a way that you need the volatile write cache, then the volatile write cache will say, I am supported on the controller. So if you take that FTP device and plug it into a non-FTP, it'll say, oh, I have a volatile write cache, and the host will know that I have to do flush commands. But if you are on an FTP capable system, the host can figure out, oh, just this one FTP configuration has a flush need. So I only need to do it if I'm using that FTP configuration. If I'm not using that FTP configuration, I don't have to do the flushes and I'm power safe. So we left that flexibility in the protocol to provide for those kind of capabilities.
Okay. Yeah. Thank you.
Good question.
Yeah, great presentations. So I also have one FTP and one key per IO question. And in terms of the FTP question, I guess two use cases were mentioned: reclaim group per die or reclaim group per drive. And I think reclaim group per drive, I mean, it's pretty straightforward and common. So I wanted to understand what's the use case really for reclaim group per die. Are there any more comments on this? What's driving this configuration?
It comes out of use cases where you've got kind of distributed storage, like disaggregated storage, cluster level storage, right? Where you've already got error correcting codes at the cluster level for availability, right? So you don't need the RAID in the drive, and the level of parallelism in a lot of these clusters is, I've got 100 or 200 writers, right? And so in those scenarios, the 8 RUH on a single super block or 8 RUH on a single reclaim group doesn't cover the parallelism that exists there. Whereas if you do have it per die, it very easily 8 RUH times 64 reclaim groups or some configuration like that very easily covers the full parallelism of those bigger distributed storage systems. So.
Okay, yeah, thank you. That helps. And then in terms of key per IO, it was mentioned that the key could be updated per namespace. So here the question is, what's the assumption then data that has been written with the old key, that it is not being accessed anymore, or is the previous key should still be available then to read previously written data?
Very good question. It's basically replacing a key into adding a new key to the key slot in the key cache. The data remains stored persistently, right? The reason you'd want to replace, say you buy a storage device that only has, for the sake of answering the question, 100 key slots, right? But you're managing storage objects that are bigger than that, you need additional keys, right? If the size of the objects are not covering entire namespaces, right, you can add additional keys and encrypt at various LBA offset with a new set of keys. But the data that's encrypted using previous keys remain and still there. If you want to access that data, you have to obviously reinsert the original keys to get that data. So there's a piece of tracking which keys associated with which storage objects on the NVM that the device has to remember and keep track, right? But that's existing capabilities today for any storage, any customer managed or host managed encryption service.
Okay, yeah, thank you.
Thank you.
One question regarding the FTP, that with FTP, that where the host be participated in the wear leveling, or is still the SSD's job?
So in the case where you have a single reclaim group, the controller is managing the writes across all of the dies, and it's managing the endurance across those appropriately. If you do more than one reclaim group and you do separate it out per die, then the host has an obligation to try to do it, but if the host doesn't do it, the controller will, and then in that case, that's why we always say it's a host hint on the placement. And host, if you don't hint correctly, the drive will protect itself and make sure that it meets the warranty of its endurance across there. Let me give you an example. You have 2 reclaim groups, and the host writes all its writes to one reclaim group. Well, that reclaim group will fill up, and we always said writes succeed, so the controller will start writing to the other reclaim group on that behalf.
I see. Okay, thank you.
Good news is we have events in there to say, hey, we did some stuff that you didn't want to do. You need to go look and see maybe you did something in your host software that you didn't want to do, and then you can go to figure out what happened.
But hosts have the privilege to do that.
Yes.
Also. Okay.
Yeah,
Thank you.
I was just going to jump in and say the same thing. The whole model on FTP is the writes. There's no new error path on writes. Works. You're not going to get a new error code back from FTP. There's logs and notifications and all this, so that when something is happening that's not ideal from a WAF perspective, the host gets knowledge of that, right? So and the drive is always expected to, when given the trade-off between honoring the hint from the host and FTP and doing the correct thing from a NAND management, read reliability, wear leveling perspective, it does the right thing from the wear leveling, NAND management perspective. So
Okay. Thank you.
Well, with that, thank you all for attending.